Welcome! In this video, I'll show you how to solve problem 7.12 as it appears in the third edition of Griffiths' Introduction to Quantum Mechanics. Now, the problem states the following. It says, if the photon had a non-zero mass, the Coulomb potential would be replaced by Yukawa potential of the form what is right here. So basically the exact same thing, but now we are multiplying it by e to the minus mu r. Now, the Yukawa potential will start appearing more and more as we start going into quantum field theory. But for now, it doesn't play much of a role, but it is good that we start looking at it. Now, notice that mu here is the mass of the photon times the speed of light divided by h bar. And usually, right, we know in real life, the mass of the photon is zero. But this is, let's say that it wasn't zero, right? Let's say that the Coulomb potential was somehow changed. And now, with a trial wave function of our own devising, we want to estimate the binding energy of this quote-unquote hydrogen atom in this potential. We can assume that mu times a is a very small number, and we should give our answer to correct to order mu a squared. So we should find, to use the variational principle, right? Our guideline, as you always, is we find our wave function, we find the expectation value of the Hamiltonian in that wave function, we minimize that expectation value with respect to some variational parameter, and we set it equal to 0. And with that, we can find the minimized energy. So first step then is to determine what this wave function is. Well, we are dealing with a hydrogen atom, and the only difference is now that the potential itself is somewhat different. So it wouldn't be too crazy to think that we could get something similar to the normal hydrogen atom, but with a different Bohr radius. So we know that in the ground state, the hydrogen atom is proportional to minus r over a. So it wouldn't be crazy now if we said, all right, let's take a and turn it into a variational parameter that we will call b, right? And for that reason, the normalization constant is now pi b cubed instead of pi a cubed, inside the square root, of course. So we could try this wave function. It's quite similar to the normal hydrogen atom, but we don't really expect there to be a behavior that is too different from what we usually see. But again, this is, just a trial wave function, so there's a lot of art involved. So now we want to build the Hamiltonian. Now the Hamiltonian is, of course, going to be the kinetic part minus h bar squared over 2m nabla squared, and then the potential, which is similar to what we're used to, except that now it has this e to the minus mu r. So we need to take the expectation value of both of these quantities. Now the kinetic part, we'll begin by solving that, and let's just write it out in general terms. So the integral over all of space, and then the wave function conjugate, but since it's real, it's going to be the same thing. So 1 over pi b cubed in the square root, e to the minus r over b. And now we get minus h bar squared over 2m nabla squared acting on e to the minus r over b divided by the square root of pi b cubed. And of course, still dr3. Okay, now we have to choose our coordinate system. So we are in a hydrogen atom, so of course choosing spherical coordinates would be best. And our operator in spherical coordinates will be 1 over r squared, d over dr, r squared, d over dr. And we wanted to act on our wave function, right? This thing right here. So we let it act on e to the minus r over b. And let's just take these normalization constant that came from the wave function and just take them out, right? Okay. Now let's begin taking derivatives. So the first part will not change at all. And then we take the derivative. So we get minus 1 over b of e to the minus r over b. Now we multiply it by r squared, so we get 1 over r squared d by dr minus r squared over b e to the minus r over b. Now we take the derivative of this. Maybe let's take out the constant, so minus 1 over b goes out, and we get 2r e to the minus r over b. And then we get another term which will be minus r squared over b, factor of e to the minus r over b. Okay, and as we did in the previous video, right, we will not be multiplying the r squared in because we will get another r squared in the outside when we write this dr3 as r squared sine theta dr d theta d phi, right? So now let's rewrite our integral and put this in there. So we get 1. Actually, we can also take the other constants out. So this minus h bar squared over 2m, we can take it out. So minus h bar squared over 2m. We also have 1 over pi b cubed. And we also have this minus 1 over b. Okay, now integral from 0 to pi, so that's theta, 0 to 2 pi, that would be phi, and 0 to infinity. And inside, we now have e to the minus 2r over b, and the r squares cancel out with the r square from the dr3, so we are left with this thing here, so 2r e to the minus r over b. Actually, I already considered the exponential, so actually I shouldn't be writing it down. Minus r squared over b. And all of this sine theta dr d phi d theta. Okay, so now there's quite a few things to do. So of course, the theta integral is pretty trivial. It's simply integral from 0 to pi of sine of theta d theta, which of course will simply be 2, right? You get minus cosine between pi and 0, and that is minus 1, so you get minus 2, which is 2. And the phi integral is simply 2 pi, so we get 4 pi, which will multiply everything. And now the other constants, let's see, the minus sign cancel out, so we get h bar squared times 4 pi divided by 2m pi b to the 4th power. And the pi's cancel out. We can simplify this a little bit, times 2. Okay, and now the remaining integral. So 0 to infinity of e to the minus 2r over b times 2r. So let me separate the integrals so that we can then solve them separately. Minus 1 over b, integral from 0 to infinity of e to the minus 2r over b r squared dr. All right, so both of these integrals look like we have to solve them by integration by parts. We could just use the formula for these sort of integrals, right? We have done it before. Maybe I'll go through it. Yeah, I think I'm gonna tell you the formula and then show you anyways, just to make sure that you, in case you don't know how to do it. So the formula for an integral that goes from 0 to infinity of e to the minus bx, this is in general, maybe I shouldn't call it b, just, I don't know, like alpha or something, minus alpha x to the n dx. This is simply n factorial and 1 over alpha to the n plus 1. Okay, pretty simple formula. So using that, this integral is simply b over 2, right, 1 over alpha, and then to the 3rd power times 2 factorial. And this one is simply, so this one would simply be b over 2 squared times 1 factorial, and that's it. Now I'm going to show you how to actually solve it in case you don't know this or you can't use it in like a test or something. So let's call this I1 or I2 and this I1. And let's begin with I2 because in the process of solving it, we will go through I1. So let me put the 2 outside. There we go. Now I2. Now this is integral from 0 to infinity of r squared e to the minus 2r over b dr. So let's integrate by parts. Let's say u is r squared, du is 2r dr, and dv is e to the minus 2r b dr. So v is going to be minus b over 2 e to the minus 2r over b. Now we multiply these two and we get, let's see, minus b over 2 r squared e to the minus 2r over b between 0 and infinity. Now this is of course 0, both at infinity and at 0, so it goes away. Now we multiply these two. We get 2 over 1 half, 2 times 1 half, which is 1, minus minus, which is plus, and b factor of, integral from 0 to infinity of e to the minus 2r over b times r dr. And this is exactly the same as I1. So let's make sure that we notice that so that we don't end up solving it twice. So I1, which is this same thing, except for the b, right? That is going to be, well, we have to use integration by parts again. So let's say u is dr, du is dr, u is r, du is dr, and dv is e to the minus 2r over b dr, and v is minus b over 2 e to the minus 2r over b. Now let's actually go for the integral. So once again, we get a term that's going to be 0, right? E to the minus 2r over b. And this, evaluated between 0 and infinity, it is 0 at both, so it's gone. Then we get minus this product, so we get minus minus, which is plus b over 2. Then integral from 0 to infinity of e to the minus 2r over b dr. Now this we can solve directly. You simply integrate it, so we get minus b squared over 4 e to the minus 2r over b between 0 and infinity. At infinity, it is 0. At 0, it is 1, but we get a minus, so we get b squared over 4. So that's our answer. And as you can see, that is exactly what we would have gotten here, right? And now we need to plug it into this other case, and we will end up getting the rest. So let's see. Right here, this was I1. So this right here is b squared over 4. And as you can see, that's exactly this, right? This is b cubed divided by 8 times 2. So b cubed over 4. So we could have just used the formulas, but, well, now we learned how to solve this. So this first one, as we mentioned, is b squared over 4, and this is b cubed over 4, but it's divided by b, so we end up getting b squared anyways. We can factor out 1 over 4. So from this and this, we can factor out b squared, right? B squared, which will partially cancel out this b down here. And then we are left with 2 minus 1, which last time I checked is 1. So this is going to be equal to, well, we can also simplify this. So we are left with h bar squared divided by 2mb squared. So now let's go for the potential. So here is the potential. So the expectation value of this, what is it going to be? Let's go off to the side here. So the expectation value of the potential is going to be the integral. Let's pull the normalization constant up front, pi b cubed. And we have e to the minus 2 mu r, to r over b. Then we have our potential, which is minus e squared 4 pi epsilon 0 times e to the minus mu r over r and dr3. So once again, let's choose spherical coordinates. Let's take our constants outside. So we get minus e squared 4 pi squared b cubed epsilon 0. We considered all of them, right? Yes. And then we integrate from 0 to pi, 0 to 2 pi, 0 to infinity of e to the... Now let's put everything together. So e to the minus r factor of mu plus 2 over b. And then we get r, what was that? R squared over r, which is simply going to be r, and sine theta dr d phi d theta. Now, the angular part will of course give us 4 pi, which will cancel out this thing partially. So that will give us minus e squared divided by pi b cubed epsilon 0. Now, what about the rest? So we still have this e to the minus r mu plus 2 over b, and then r dr, and the integral goes from 0 to infinity. So this is what we now have to integrate. Well, this isn't particularly difficult of an integral. We can solve it easily by using integration by parts. So let's call it I, and let's use integration by parts. Just for simplicity, and for now, I will call this alpha or something, because I don't want to have to write it the entire time. So let's say u is going to be r, du is dr, dv is e to the minus r times alpha dr, and v will be minus e to the minus r alpha over alpha. So the first part of the integral will be the product of those two. So we get minus r over alpha e to the minus r alpha between 0 and infinity. This is 0 once again, right? 0 at infinity and 0 at 0. Minus this product, so we get a plus 1 over alpha integral from 0 to infinity of e to the minus r alpha dr. Now this is quite a simple one. We get minus 1 over alpha squared e to the minus r alpha between 0 and infinity. Now, of course, at infinity, it's going to be 0. So this integral will be only at 0. So we get a minus sign in front. So we get 1 over alpha squared. All right. I guess we could have used it, done it using the formula as well. Well, whatever. We already did it. So plugging it back in. We are left with, so I said 1 over alpha squared. All right, and what was alpha? I think there it is. So alpha was mu plus 2b. So 1 over mu plus 2b squared. Wait, no, 2 over b. 2 over b, sorry, 2 over b squared. So now let's just do some algebra. Let's take minimum common denominator here so we can simplify it. So the first part will be the same, pi b cubed epsilon 0. But now this thing right here will be 1 over mu b plus 2 divided by b, and all of this squared. So we can now write the like that. write the b up here, right? And thus we can simplify it a little bit with this b. So this is our result. This is the expectation value of the potential. So now let's put everything together. Now let's do it somewhere over here. So the expectation value of the Hamiltonian, which of course is the expectation value of the kinetic part plus the expectation value of the potential, will be, now what was the expectation value of the potential? It was actually here, h bar squared divided by 2mb squared. So h bar squared divided by 2mb squared. And the potential, which we just found, is, okay, it's negative, so minus e squared divided by pi b epsilon 0, and then 1 over mu b plus 2 squared. Okay, so this is the Hamiltonian, the expectation value of the Hamiltonian, which is the energy. But we want to minimize this. We want to find the least possible value for the energy of the ground state. So we have to now take the derivative of this with respect to b and set it equal to 0. So this first part, we have b to the minus 2, so we get minus 2 h bar squared divided by 2m, and now it is b cubed. So the 2's cancel out. Now, to derive this, I would like to rewrite it, because I get confused when I have to derive things in the denominator, and especially if there's a product rule involved. So I like to do it like this. Now, of course, you don't have to do this, but this is the way I like to do it. So derivative with respect to b of b to the minus 1 times mu b plus 2 to the minus 2. I do recommend this because it is kind of foolproof, and I'm good at making dumb mistakes. So this is honestly worked great for me. Now I'm gonna use the opportunity and write this to the left hand side. So we get h bar squared mb cubed, and this is now equal to this thing. So minus e squared pi epsilon 0, and the derivative. So derivative of the first part, b to the minus 1, we simply get minus b to the minus 2 times everything else. Then we have plus, now b to the minus 1 times the derivative of this, which is going to be minus 2 times this entire thing to the minus 3 times the derivative of the inside, which is going to be mu, right? This is simply the chain rule. Okay. So now let's try to rewrite this a little bit better. So I'm going to leave everything else b. So h bar squared mb cubed. This is equal to minus e squared pi epsilon 0. And let's see, what about this? So let's go for common denominator. So we can see we have b's and mu b. So actually, let's write it like this. So we have minus 1 divided by b squared mu b plus 2 squared plus, actually there's another minus, so I guess minus. So minus 2 times mu divided by b times mu b plus 2 cubed. So you can see that if we take common denominator, we can simplify this a little bit. We can also put this inside, so we get rid of the minus signs. So now let's take common denominator. So once again, h bar squared mb cubed. This is equal to e squared pi epsilon 0. Interesting epsilon, but okay, so we need to multiply this by mu times b plus 2, and we need to multiply the other side by, let's see, only b, right? 2 mu b. And then we will have b squared mu b plus 2 cubed. Okay. Now, so of course we can now add this and we get 3 mu b plus 2. And what else can we do? And now we could do the following. So we have mu b plus 2, we have mu b plus 2. We could go ahead and factor out the 2, for example. And yeah, let's do that, because what this is looking like, maybe I should introduce it in a little bit because it's going to be more apparent. Yeah, I'm gonna wait a few steps before I do that so that it becomes more apparent why I'm going to do it. Okay, so what we are looking for here is b, right? We want to find b, that is our objective. So, well, first of all, b is not going to be 0, of course, so we can multiply by b and we get rid of that. So now let's multiply b to the right side and these constants to the left. So we got h bar squared pi epsilon 0 divided by m e squared. This is equal to, and then we have b times 3 mu b plus 2 divided by mu b plus 2 cubed. Okay. So as you can see, oh, sorry, I wrote b as a subscript. So as you can see, finding b is not going to be easy. But we could do is write out an expansion of this, right? So what we have here, we can write as an expansion, because mu b is very small and it is to the third power, so we're going to get very, very small terms, so we can go for an approximation. But to do that, we would really like to write this in the form of 1 plus x, right? So to do that, and this is why I was saying it before, we need to factor out this 2. So let's factor it out. So if we factor it out, we will have 1. This will be divided by 2, and then we will be factoring out 2 cubed, right? So that's where we are at. And now let's see. We have 2 cubed, which is 8, and there's a few things we can do. So if you look at this thing right here, it is a big mess, but we can make it look a little bit better. So let me see, I have it written down somewhere over here. So as you might recall, the Bohr radius A is 4 pi epsilon 0 h bar squared divided by mass of the electron E squared. So it's basically the exact same thing, except that we are missing a 4. But here we have an 8, which is 4 times 2. So if we multiply both sides by 4, we get rid of this, and now we have it here. So now we can rewrite this entire thing in the circle with simply A, the Bohr radius. Okay, so that makes things a bit easier. And now we can simplify the notation a bit further if we take this 1/2 and multiply it in here. So we get 1 plus 3 mu b over 2. Okay, so now that we simplified our notation, we must begin simplifying this expression. So our first task will be, I'm going to do it to the side, I guess, will be to take this mu b over 2 plus 1, which is to the minus third power, and now we want to expand it. So how exactly does one do that? So you might recall the formula of the binomial theorem, which is exactly what we have to use here. So to expand this in general, we have to use the binomial theorem. And we know that, right, the generalized 1 plus x to some minus n power will be 1 minus n times x plus n times n plus 1 divided by 2 factorial times x squared, and then minus, well, some higher order. We don't want to go over the mu b squared, so we don't, and mu b is our x, right? So we don't really care about these higher order terms. So using this, our n is 3, so we get 1 minus 3 times x, which is mu b over 2, plus 3 times the n is 3, so we get 3 plus 1, so that's 4 divided by 2, so we get 12 over 2, which is 6. Whoops, that's... So 6 mu b, and this thing is squared. Okay, so this is our expansion. So, and actually I guess we can simplify this as well, right? So 3 over 2. So we can now plug this instead of this. So instead of having that dividing, we can now write it as the product of this and what we just found, which was 1, and I don't remember the rest, minus 3 mu b over 2 plus 3 over 2 mu b squared. So that is what we now found. So this is what our expression looks like. Now we can multiply through. So a is b times. Now let's multiply through. So we get 1 minus 3 mu b over 2 plus 3 halves of mu b squared. And then we start multiplying here. So 3 over 2 mu b. And then this one. So we get minus 9 over 4 mu b squared. And this term is of third order, right? It's mu b cubed, which is so small that we don't need to worry about it. So this term will cancel out this one, and then we have the sum of these two. So that will be 6 over 4 minus 9 over 4. So we get that a is equal to b, 1 minus, so 6 minus 9, we get minus, actually I already considered the minus, so minus 3 over 4 mu b squared. So that's what we have. Now the problem, however, is that, well, this isn't really a formula for b yet. What we need is to have b equal something. So let's divide by that squared bracket. So we get b is equal to a divided by 1 minus 3 over 4 mu b squared. And now let's expand again this thing, which is it is basically to the minus 1 power, right? So we get, well, I'm gonna do it here off to the side. So we have 1 minus 3 over 4 mu b squared, and all of this to the minus 1. Now using the exact same formula as before, right, that 1 plus x to the minus 1, once again this is simply the binomial theorem, sorry, this is to the minus n. Of course n will be will be 1, but in general it's going to be 1 minus nx divided by 1 factorial, right, plus n times n plus 1 divided by 2 factorial x squared, and so on. Now the other terms are too high, so they won't matter. So let's see, 1, then we have minus n, which is 1, times x, which is minus this. So we will actually have a plus now, 3 over 4 mu b squared. And now the next is x squared, but this is already squared. So we would get mu b to the 4th, which is way too large. So this is already a good approximation. So this is approximately, right, a 1 plus 3 over 4 mu b squared. Okay, so what we're saying is that this thing is b, but take a look at this. This is basically a plus a very small number, because it is of the order of mu squared, right? And that means that that a is very, very, very close to a. So for that reason, we can approximate this b in here as A. So that way we can find a very good formula for B, which is exactly this. Of course, it is an approximate formula, right? So what we did there is that, yeah, because B is basically A plus some very small factor. In that small factor, we said, all right, this is the same as B. It's going to make a very small difference, so might as well put it in there, and we will get a very reasonable result. So this is our value for B. Now we have to plug it in to our Hamiltonian, which is up there. So maybe I'm going to rewrite my Hamiltonian down here. I think that's going to be easier. So our Hamiltonian is going to be, so H, let me see if I can copy it from here, from my notes. That would make it a bit easier. So here, so the expectation value of the Hamiltonian was h bar squared 2mb squared minus e squared 4 pi epsilon 0 1 over b, and we had 1 plus mu b over 2 squared, right? Let me double check. Minus e squared b, yeah, we hadn't done the factorization back then, but we already did it now, so it's okay. The only difference is that this 2 wasn't factored out before. Okay, so now let's plug in the value for b. So the expectation value of h, now that we have found the minimized b, right? That's what we're doing. 2m, and now 1 over b squared. So 1 over a squared 1 plus 3 over 4 mu a squared squared minus e squared over 4 pi epsilon 0. And then we have 1 over b, which is 1 over, let's see, 1 over a. And then we have 1 plus 3 over 4 mu a squared to the minus 1. I'm going to write it like this because we are going to end up expanding soon. Otherwise, we can't really simplify it at all. And then we have 1 over 1 plus mu b over 2 squared. So that would be 1 plus mu over 2 times b. So, and b is a times this. It's basically this, but not squared. So we get another a here. And then we have 1 plus 3 over 4 mu a squared. And this is to the minus 2. But notice, right, that once we multiply here, we're going to get the following. We get mu a over 2, but then we get mu a cubed. So this thing, actually, we can simply write it as 1 plus mu a over 2. Because the next term was going to be of higher order, right? Of mu a cubed, which is so small, it makes literally no difference. Okay, so now let's begin simplifying this. Now, how could we do that? Well, let's plug in the value of a. So we know that a is 4 pi epsilon 0 h bar squared over me squared. So 1 over a squared is m squared e to the 4th power 4 pi epsilon 0 squared h bar squared squared. So we can simplify this a little bit. So this gives us h bar squared when we simplify it with that. M cancels out that. And what do we have left? What we have left is this. So 1/2 m e to the 4th h bar squared 4 pi epsilon 0 squared. What is that? Well, as you might recall, E1, the ground state energy for the hydrogen atom, is m over 2 h bar squared e squared over 4 pi epsilon 0 squared, which is precisely what we have here. So the, well, minus this, of course, minus. So minus this. So this entire thing is simply minus E1 times this bracket here. So 1 plus 3 over 4 mu a squared to the minus 2. But what is this bracket? We can expand it. So 1 plus 3 over 4 mu a squared to the minus 2. We can expand this, and it is 1 minus n, which is 2, times 3 over 4 mu a squared. And well, this and any higher order terms are way too small, right? So we stop here. So this thing right here we can rewrite as now 1 minus 3 over 2 mu a squared. And now we can move on to the next part. So now we move on to this. So minus e squared over 4 pi epsilon 0 and 1 over a, but we know what a is, so let's plug it in. So a is mass of the electron times e squared 4 pi epsilon 0 h bar squared. But this is twice the energy of the ground state of the electron, right? Minus 2 times. So we can now, exactly as before, we get rid of this and we replace it but with minus 2 times, so plus 2e1. And now we plug in everything else. So then we have 1 plus 3 over 4 mu a squared to the minus 1. But what is this? Let's expand it. So this is simply going to be 1 minus 3 over 4 mu a squared. And any higher order terms are going to be negligible. So basically, we put a minus sign in there. Now, for the other term in the bracket, we get 1 plus me squared to the minus 2. This is 1 minus 2 times mu a over 2. Am I right? Yeah. So these things cancel out. So this cancels out this. And the next term would be plus, and then we get 2 times 2 plus 1, which would be 3 divided by 2 factorial times mu a over 2 squared. Right? Yes. So this would mean these two cancel out, and we are left with 3 over 4, considering this one. Okay, so let's plug it in. We get 1 minus mu a plus 3 over 4 mu a squared. So now we need to multiply all of this. So in the first term, there isn't really much more to do, right? It's done already. It's ready. So minus E1 plus 3 halves mu a squared times E1, of course. And then here we have plus 2 times E1. So when we combine that with this part, it becomes positive. So well, I guess I could have just deleted the minus sign. Then we have, okay, I went a little bit ahead, so maybe, okay, so we get 2e1 times 1 minus mu a plus 3 over 4 mu a squared minus 3 over 4 mu a squared. And now the other two products don't make any difference, so these two cancel out, this with this. So now what we are left with is going to be 2e1 minus e1, so just e1. And then we have minus 2 mu a e1 plus 3 over 2 mu a squared e1. So basically, the result is going to be 1 minus 2 mu a plus 3 over 2 mu a squared. All of this times E1. So this is the energy that the hydrogen atom would have if the photon was not massless. Of course, if mu goes back to 0, we get back the result E1. So yeah, it was a bit of work, but it was mainly a lot of algebra, right? The integrals weren't really that difficult. It was mainly about coming up with the trial function and then just going for algebra and having a lot of fun with it. So I hope this was useful. If it was, please do make sure to leave a like on the video, comment, and subscribe. It doesn't cost you anything, but it really helps me out a lot so I can continue to make these videos. So I'll see you in the next one. Thank you very much for watching.